Okay, so we're going to be finishing up the workbook with 14.8. So let's take a look at this problem. So a strip of metal, X, we'll call it X. It's in a solution that has Y2 plus ions. Okay, so we got our little container, and inside the container, we got Y2 plus ions. You put a piece of metal in there, and this is X. Okay. And then there's no reaction. Okay. There is no reaction. All right, and then there's another container. So we put X inside another container. Okay, and the other container contains Z2 plus ions. Okay, so we put the same metal in a different container, and there is a reaction. Okay, and so what's going to happen is Z is going to plate out or solidify on the surface of X. Okay, so far makes sense? Okay, so this is kind of the scenario that we are talking about. And so based on that information, we're basically trying to figure out the reduction potentials for these three metals, X, Y, and Z. Okay, so far so good? All right, so basically you're just trying to figure out which one reduces better. So I'm going to give you guys 2 minutes just to kind of think about it, maybe talk about it with the person next to you. See if you guys can start organizing it. And yeah, and then we'll go over in about 2 minutes. Okay, so if you guys remember, reduction is gain, right? So whatever has a higher reduction potential means that it's better at gaining electrons. Okay, does that make sense? So the higher the reduction potential, the better it is at stealing electrons from other metals. Okay, so let's just take a look at these ions. So let's take a look at Z2 plus first. So in order for Z2 plus to turn into solid zinc, is it going to be gaining or losing electrons? Gaining, right? It needs to gain 2 electrons, and it would get the electrons from X, right? So if we compare Z and X, which one has a higher reduction potential? Z, yeah, Z is going to be more reducing, okay, because it is able to steal electrons from X, and that's how it goes from aqueous to solid form. Does that make sense? Okay, so Z has to be the first one, and then you can kind of tell just by looking at that what the correct answer is. Okay, another way that you guys could have thought of it is Y cannot steal electrons from X, right? So that means that X is more reducing than Y. And so you can also look for the one that has X higher than Y, and it's only this one right here. Okay, so Z is the most reducing out of these three, X is in the middle, and Y is the least reducing because it can't steal electrons from nobody. Okay, make sense? So that's how we can look at problems that have reduction potential. And again, you'll need to be comfortable with this since the FRQ will be a galvanic cell problem, which we'll do next. But any questions? Easy peasy? Lemon squeezy. Alrighty, let's go on to 14.9. All right, so hopefully you have this on your Chromebook so that you guys don't have to like squint up to see this. Okay, but we have a galvanic cell and we got 2 standard half cells. Okay, and then this is the net ionic equation for this cell. Okay. Oops. Okay. All right, so what we're going to be doing first is let's just kind of go through this system and let's label some information that we've learned. Okay, so let's talk about the flow of the electrons. Okay, which direction do the electrons flow? Positive to negative or negative to positive? Yeah, negative to positive. Hold on. All right, anyway, like we said, electrons flow from negative, okay, to positive. Okay, make sense?
Yes.
All right, now let's name them. So on the what is the negative cell called? Yeah, anode. Yeah, anode. Okay, and then the positive one is the cathode. Okay, easy way to remember this. Remember cations, anions. Remember cats are good. They're positive, and Annie is bad because she broke my heart in kindergarten. Okay. No, I just made that up. But now you're not gonna forget it. Okay. So cathode, anode. Okay. A couple other things. Which side does oxidation take place? The anode. Okay. Another way that you could think about it, again, remember oil rig, right? Okay, so remember, just think about what happens in the half reactions. And then on the right side, the cathode is where reduction takes place. Okay? So far, so good? So for galvanic cells, just for the AP test and for our exam next week, just memorize this. It'll make it so much easier. Okay? All right. So now we can start working on the actual problem. Okay? So let's take a look at part A. It's asking what is Y and Y2 plus. So now we know that it's on the cathode side and it's reducing. So we can take a look at this reaction and figure out which one is being oxidized and which one is being reduced. So let's take a look at CD first, cadmium, and let's figure out if this is being oxidized or reduced, right? So it starts as a solid and turns into an ion. So is it gaining or losing electrons? It is losing electrons, which means it is oxidized, right? Okay, and then obviously that means the other one is going to be reduced. Okay, so just based on that information, just by knowing this right here, we can basically figure out most of the problem. We know that on this side, the oxidizing side, this is CD. Okay, and then we got CD2 plus, which means that our answer for Y is going to be, it is PB, it's lead. Okay, so that's your answer. For part A, Y is PB solid, and Y2 plus is PB ion, and it's aqueous. Okay. Easy, right? Galvanic sounds are so easy. Super easy. This is boring. All right. One thing I do want to mention that I kind of touched upon this earlier, but remember the salt bridge? You guys were talking about the purpose of the salt bridge. Basically, let's say, for example, this salt bridge was made out of potassium nitrate, so KNO3. Okay. So the way that the salt bridge helps facilitate the flow of the electrons is that the components of the salt bridge are going to move in between them. Okay, talk about that a little bit more in a second, but just keep that in mind. The components of the salt bridge are going to move, but we'll get to that in a sec. So we'll go to part B now, initial concentration. So for this right here, if you take a look at the problem, it says that the initial concentration, or this galvanic cell is standard, right? You guys see that in the problem above? Okay, so if it is standard, it means that it is always going to be, the concentration for everything is 1 molarity. Okay, that's just something you guys got to memorize. It's like a constant value. STP is a certain constant stuff. Standard cells are 1 molarity concentration. That's something you'll probably have to memorize as well. Okay. Okay, and then we did see already, right? We know that the cathode is going to be PB. And your anode is going to be CD. Okay. So far, so good? All right, so let's go back to the salt bridge. So now that we have all this info, let's talk about what moves in the salt bridge. Basically, what is going to happen is that we want to take a look at what the salt bridge is made out of. The salt bridge is made out of KNO3, and the ions are K plus and NO3 minus, right? So basically what's going to happen is that the anion that makes up the salt bridge is going to move towards the anode. Okay, and you guys probably want to memorize this. Okay, the negative component of the salt bridge, the anion, will move into the anode. Okay, so the salt bridge, basically, the thing that makes up the salt bridge is going to break down. It's going to ionize, and it's going to supply the negative ions to the anode. Okay, and that's how it keeps the flow moving. That's how the electrons keep moving throughout the cell. And then conversely, the cation is going to move from the salt bridge towards the cathode. Okay.
Is that always a strong electrode?
Yes. Yes. Good question. Yeah, because you want to make it as easy as possible for it to solve. Okay, so yes.
That was because the electrons are like going to the cathode. So
Yeah, it needs to move back into the anode. Yeah, so when you run out of your salt bridge, then the flow will stop and then the battery's dead. Okay. Alrighty. That's pretty much, I think, all the info you guys need for galvanic cells. If I forgot something, make sure you do your reading, which all of you guys do, right?
Yes.
Yeah, but that's at least that's definitely all the major components of it. Am I?
can you just like read everything to us?
Just read the book to you,
Yeah.
bro. You guys already like fall asleep me talking to you. No, I'm good. I don't. My voice isn't nice enough. I have like. No, I'm good. All right. So let's go to part D now. So for part D, I'm gonna scroll down a little. We're gonna write the balanced equation for the half reaction that happens at the cathode and the anode. So here we're gonna be writing the half reactions. So I'm gonna give you guys put a little more space, but take about a minute. See if you guys can take the original equation and write the half reactions that take place. And then it tells you the electrical potentials for the cathode and anode. And I want you guys to just put that on the side, depending on which half reaction happens on the cathode and which reaction happens at the anode. Okay, take about 2 minutes to write the half reactions. And then after you label the electrical potentials, I want you guys to calculate the standard cell potential. Okay, so for the equation, I'll just give it to you guys. For the oxidation, it should be solid cadmium, and it's going to ionize, and 2 electrons. Okay. And remember, oil rig, it is losing electrons, so it's separating from the electrons. Okay. All right, so we go to reduction now. The reduction is going to be for the lead, the ionized lead. It's going to gain 2 electrons, and then it's going to become solid. All right, so that's what you should get for your half reactions. Oh, yeah, you could do that. Yeah. Yeah, you really don't need to add the states of matter. It's not a big deal because if it's ionized, it's kind of assumed that it's aqueous. Okay, so I wouldn't take off points. I don't think the AP test will take off points either. Yeah. Okay. All right, and then for the anode, we know that the anode is where oxidation takes place. So this would apply to this equation. And then for the cathode, it is reduction. So it apply to this equation. Okay. So you just need to label it on the side. All right, and then for the standard cell potential, super easy. You just need to take the values for E and then just add them up. So you can get 0.4 plus negative 0.13, or you can just subtract it. And then that should give you 0.27 volts. That's it. And congrats, guys. That's all the stuff that we're really going to go over for the year. If you want, yeah, go ahead. Bye, guys. You're free. Yeah.